Can you see my screen?
Yes.
So we have our platform is a MATLAB application. So we have to open the MATLAB first of all, and then we move to the very simple software. We choose the folder with the program, and then okay, and then the program is running. Have to wait a little in order to open the program. This program, the coding is very extensive. The code is very extensive. We have many algorithms in this software, and you can do almost everything. If you have actually, if you have any question, we can try to check it with this software. We run the program, and now we have the graphical user interface. The graphical user interface is another tool of this software. The code can be run without the GUI, but the GUI is a friendly for a user that is not well known for coding. So the first part is to upload or an image or a set of images or a project where we worked in previous days or time, or a simulation dataset. You can import datasets from stem cell beam here, but we can change the code to upload another from datasets from another simulation software to upload.
And I should add that here that stem cell beam is a software for image simulation of stem images. Yes.
Yes. So in this case, I will show you, in this case, a case from stem cell beam. Actually, we have a case with one monolayer indium gallium nitride quantum well. We have also, when you input an image from image simulations, the software have this window in order to input the detector sensitivity. If you have the detector sensitivity, then you upload them. It's very easy. And so now we have the images. The first part, the workflow, is on the left. You can by moving from the up to down, you can perform our analysis. The first part is the images, and we have to convolute the images with the full width half maximum of the source size. This is performed in order to have a direct comparison between experimental images and simulated images. So by convolute a Gaussian function here, like we simulate actually the source size, and as you can see, we have a set of images with different thicknesses, and you can see how the intensity is changed by changing the thickness. The other parts of this menu, from image menu, is about experimental image. The contrast is about to find the contrast numbers of experimental images, and Bragg filtering and PCA filtering are powerful filters to perform noise reduction. So let's move first in the lattice analysis, actually the strain analysis. The first part is to insert the set of sublattice, actually the peaks, is a group of peaks. And here we can perform the peak fit. Actually, in each menu, we follow the up-down workflow from up to down. The peak fit menu, we have to change to set here the number of the CPUs. in order to make it parallel and is more fast than the other with one CPU. And the mean separation distance is the distance between the peaks. In order to find the first peaks, the first bright spot with the highest intensity in multiple images with a distance between them at higher than 8 pixels. So you can see here that we have many peaks, but as you can see, we have a peak here. It's not. This is not a problem for us. We can select only this pixel and remove the first peak finding is only to determine the initial positions. It's not crucial for the other work. We have to check now all the possible location of the peaks. You can see here that we have another peak here that is not in the position we want. So we now remove this, and you can see that we have some peaks here that the program doesn't find due to the edges of the image. So it is very easy for us to add manually the peaks, the initial peaks. Okay, here, add peaks. And now we have in all images, in this case, the peak positions. So now we have to move to the refinement process. So we have to fit one 2D Gaussian in its fit, and with the model 1 or 2. The model 1 is by fitting a 2D elliptical Gaussian function, while the model 2 to fit a Gaussian and symmetrical Gaussian 2D Gaussian function. So in this image we have, as you can see, symmetrical spots. So we use this one. So we click the fit, and the program makes the calculations in order to find. As you can see here, we have a button to see if the program is running or it's ready for the next step, for the next analysis. We have to wait not so much. Actually, we have here, as you can see, 6 with 16 peaks in each image. So we have almost 100 peaks in one image, and we have almost 100 slices. So the program now fits 10,000 peaks, 10,000 2D Gaussians in this dataset. It takes 1 minute at least, and you can see that the peaks now are defined, are very well defined by the program. Of course, I have to mention that the intensity weighted center of mass is performed in the initial part before the fitting of 2D Gaussian. So now we have the peaks. You can save this data as peaks, and the only way, and the only part you have to do is to go here, file, and save to, and define a region, a folder you want to save the data. For example, here, figure data, and when we go here, we can see that we have all the local peaks in pixels and the positions. The data 6 and data 7 and the number corresponds to the number of the slice here. After that, the next step is to find high symmetry axes. Actually, with the program, this is a very clever algorithm to find the periodicity you want along different angles and different directions. This tool is automatic. The program runs and finds all the possible directions, but all the possible high symmetry axes in these images. We have to wait a little bit here, and after that, the next step is to group the peaks in sublattices. But firstly, okay, you can see here that the program gave us the angle and the period, and the planes are given here. So all these planes are not crystallographically correct, but they are high symmetry axes only. We have to choose from them only the one we want. So in our material, we have to check the one with the four plane, and the one with the 7. As you can see, they are the groups, these groups. So the other axes are deleted. And we have only the chosen axis, this one and this one. Actually, now we have groups of atoms. Here, another part is to define the reference area to use in the next steps in strain analysis. So we have to select reference. We make here a ROI. We choose the region. We have the capability to change different reference area, and where we know we have a pure material. Here we have gallium nitride. The monolayer is in the center. So we push this button, select a reference, and now we have the information about this reference area. The next step is to define the strain. So we have two axes, 1 and 2, and we calculate the strain. The strain is here. So as you can see, actually the program has the capabilities to use different colors in order to check, to see better the features, the structural features. You can see here that we have multiple capabilities to describe the peak positions. Wait. With boxes, with circles, with maps. Here we have the local peaks. The distances between the peaks are given here. We have now the distances and in pixels, and of course we can save all this data in our folder. The most important part is the strain along y-axis and z-axis. You can see here that the strain He is 0 due to the fact that this quantum well is biaxially strained on the gallium nitride barrier, but the strain psi along the vertical axis is changed, as you can see here, by having a different behavior. This strain, the strain behavior of these materials can be checked by choosing this monolayer average, but on the proper axis. So the planes are here. You can see here that we have the planes number 2. So by performing an averaging along this direction, we have the average strain in each one. So monolayer average, and now we have the strain for each monolayer. This is the central monolayer, and this is the next one. This is the strain behavior, the strain of such materials. By changing now again in the scatter circle, we can choose also a region of from here, which I choose now only this region. This is the central one. We keep only this. We perform a monolayer average, and by averaging this, we have the strain value in the central monolayer in all thicknesses. This is the first slice, and this is the last slide. So we can see that here we have a strain 7.3%, and it's a value close to the expected one from the molecular dynamics. So now let's move to the other part. We can restore the data in order to have all the data here. And after the strain, the next part is to calculate the composition using the intensity, high resolution STEM. Here, firstly, we divide the image in, actually we make more discrete the image in order to avoid stepped Voronoi. We want to have continuous edges and not no stepped edges. So we use a grid factor here. Wait. Sorry, my display is closed. And here we have the intensity. We perform Voronoi tessellation, and the intensity is measured in each Voronoi. Calculate intensity. The program is busy. For each peak, we found in the previous steps, we assign a Voronoi cell, and the intensity is measured as the average of this Voronoi area. This is the first step of intensity analysis in high resolution STEM images. This is a time-consuming procedure. We have to wait a little in order to find all the Voronoi cells and have the maps of the Voronoi with intensities. And after this, we can determine the other parts. You have to wait here a little bit. If you want to make it faster, you can you can leave the image as it is, and you don't use the grid factor. You have to wait more. The other menus here are to perform the fit intensity in regions with known composition. The thickness is to find the thickness in the areas you want. And the last part, the composition, is to determine the composition by using a database. Actually, I will show you now how we can create this database. Okay, here. And I will show you how how you can create the database and how you can employ this database to our analysis. Okay, let's make it this color to have. You can see here that you have the quantum well in the center with different intensity. The next step is to define the intensity in the intensity regions with known composition. So we perform a 2D analysis And because here we have a database from, we have a data set from simulations, we know we have an error here because I didn't upload the database file. So we have to actually this software has the ability to show you which is the error and what you can do in these cases. So we have now to upload the database. The database is a folder. I will show you how is defined this folder. You can select the folder, and after that, form this. And we have now, as you can see here, the intensity ratio. So in these images now, we have the intensity ratio. So by performing a monolayer average along the plane number 2, you can see that for each image, we have a curve like this, and the central one shows us the intensity ratio here. Wait, let's go to maps. Another, the proper way to construct the database is to perform a selection of area. Here we have the quantum well, to keep only this and perform monolayer average here. By averaging this value in all slices, you can have this diagram which shows us how the intensity ratio changes by changing the thickness. If the structural model has a fixed composition, then this graph provides us the information about the behavior of one monolayer thick quantum well with known composition, and can be used directly can be used as database now. So let's move now to, and of course you can say you have the opportunity, the ability to save all this data in TXT files and use it and use after the analysis. Now, and move in this restore data in order to have all the database. The data is here. So the next one is to find the thickness. Here we know the thickness due to the fact that we have image simulation. So we use image simulations, and the thickness tab here, you can see that we have the intensity tab, the intensity fit, the thickness. Here you can see the thickness. We have 120 nanometer thickness. So the next part and the final part is to determine the composition. Here. So we have in this menu we have multiple different methods to analyze the composition. Actually, in this window we try to perform to make a continuum behavior of the color maps I showed you in my presentation. Actually, we tried to connect discrete data of thicknesses and discrete data of composition in order to have a continuum behavior of such materials. So in this case, the most appropriate way is to interpolate linear and fit to the second degree inverse polynomial. And by calculate the composition, the software tries to translate the intensity of its Voronoi cell to an indium composition by considering the thickness that found in the previous step. In this, I will show you now, because this is the most time-consuming procedure in our software, and due to this, I will show you now what is a database and what we try to make with this tab. The database consists different txt files with name, ratio, and a number. The number here, the ratio, is referred to the composition, to the reference composition. So a ratio 50% has the data about the intensity ratio and the composition. If we have a quantum well with thickness 1 monolayer and the composition 50%, then we know from simulations that the expected that the intensity ratio is these values for each image, for its thickness. And the concept of this tab here is to connect now not only data with not only the data with with different thicknesses, but connect data with different compositions. It's actually, wait a minute to open my presentation. Let's see firstly if we have not yet. So wait to show you what we try. Wait. Okay. So all this database is important to create these maps. And the tab here, the tab the last tab I used tried to connect the data with different compositions and find this red line. Actually, this is the procedure. If we find this behavior for its thickness, then we are able to find the composition in its Voronoi cell. Let's wait. We have to wait a little bit. If you want to ask something here that we have time, I'm open for questions.
Isaac.
Yes. Hello, Julita.
Hi. I would like to ask about this because next to this InGaN monolayer, there is visible like an extra, layer.
Yes.
Is it nitrogen or what is it actually?
Okay, exactly. Close to in the central quantum well.
Yes. Mm-hmm.
Nitrogen. It's nitrogen.
Okay, so this is nitrogen. And why it is visible for this monolayer and it's not visible for other?
The reason is that we have here nitrogen that are connected with indiums and not in gallium. So these nitrogen atoms have different static atomic displacements. Actually, each atom in the simulation we have to take into account the static atomic displacement. We have to take into account how to vibrate these atoms around the central position. Here we have nitrogen atoms close to the atoms, to the indium atoms, and they have different value of this parameter.
Okay. Thank you. Thanks.
Thanks.
So it's a nice example that since these nitrogens are visible for when they are connected to the indium, but they are not visible when they are connected to the gallium, how the local environment can influence your composition that you are seeing. So this is why you need the image simulation.
Exactly. Have to wait a little bit. Of course, if you want to perform a not so strict analysis, you can use a different method here. You can use a 2D polynomial fitting in order to find the behavior of intensity ratio with different thicknesses and composition. But in our case, this choice was the only way to have very accurate results. And I will show you what I mean, very accurate results. Actually, simulation, in this simulation, we have one monolayer quantum well with a random distribution of atoms, and the nominal composition is close to 75%. The database was created using other boxes. So if we perform a very accurate analysis, then the composition in this quantum well must be close to 75% in indium. It is important to have the same methodology from the start to the end. As you measure, and now we have the positions, and now you can see that the intensity ratio is translated to composition. The first part you have to check is the monolayer average, and as you can see, we have here a composition 74%. We expect the composition 75%, but we have also a random distribution of atoms, so it is possible to have values like that. Another part of this, another ability of this software is to choose only this. Choose only this this quantum well, perform a monolayer average. Choose this area, keep only them, perform an average and average. As you can see here, actually I chose only the central quantum well, and our analysis showed that the composition of this quantum well is 74%, and this is the composition for each image. Each image was analyzed, and you can find the composition in the quantum well in each image. In these initial images, the first images, the thickness is very low, so the atoms are randomly distributed, and we don't have the nominal composition. So by increasing the thickness, the composition is stabilized, and you can see that we have a composition close to the nominal one. So this is a test to see if our methodology is correct or not. Another ability this work is to choose only, this is useful for defects, for example, to choose only one of them, to keep one of them, to perform monolayer average, and you can see that the atomic column here, due to random distribution of atoms, only this atomic column does not have a composition close to the nominal one, but it increases when the thickness is increasing. Actually, you can choose regions as you want. You can use the freehand tool to choose only the regions you want. You can keep only this region, and this can be used in crystalline materials, in clusters, and you can determine the composition in different shape areas. So I think that we can, this is the final part of this analysis. The other the other tabs here, GPA and detector, are referred to the GPA analysis and the detector analysis in order to find the sensitivity of the detector. And you can add other tools here in order to perform other analysis. If you have any question about this software, I'm open for that.
Thank you, Isaac, very much for this informative analysis. These two students have done quite a lot of work. We're going to have it publicly available very soon on GitHub, and we hope that we can interact with the community to improve further this approach. So maybe if you want to ask something about this software, or you want to suggest things that you may want us to add to make it more friendly to you or more useful, we are open to suggestions. Okay. I hope you liked it. It had many features. It's not always necessary to use the whole thing. You can use the parts that are interesting to your problem. So we showed this for a very extreme case, just one atomic monolayer, but of course you can use it for quantum wells, quantum disks, in nanowires, whatever is your system, or nanoparticles, for example. Yeah. Okay. So I see no questions. Maybe it was too much. Right. So I think, yeah, it's been 1 hour and a half, no, 2 hours. So I think maybe it's time to stop this webinar. And yeah, you can keep in touch and ask us any questions that you may have by email, for example, or give us any suggestions.